box is to be made out of a square piece of cardboard. Which is 10 inches on each side. The square piece of cardboard. 10 inches by 10 inches. And the way you're going to make this box is to be made out of a square piece of cardboard by cutting smaller squares out of equal size out of each corner. So you're going to cut squares of equal size out of each corner of this cardboard and then fold up the remaining flaps. So this is actually a problem that you should have seen in 126, or the setup for a problem that you should have seen in 126. And kind of the question in 126 was to build a formula for the volume, build a function for the volume of the box. The question here is a little bit more complicated in that you're supposed to find the length of square to cut to maximize the volume of the box. So we want to maximize the volume here. Find the length of square to cut out that maximizes the volume of the box. So this is optimization. This is a typical optimization problem. So optimizing something means you're going to have to maximize or minimize some function. And usually you're going to have to build that function on your own. You're going to have to somehow come up with the formula. So in this case, I've described this situation on how we build a box. And I want you to come up with the formula for the volume of the box and then find the length of the square to cut out that will maximize that volume. So first we got to make sure we understand what's going on. So let me draw you a picture. A box is to be made out of a square piece of cardboard. Okay, this is square. It's 10 inches by 10 inches, so this is 10, this is 10. By cutting squares of equal size out of each corner. So out of each corner, you're going to cut a square. Now we don't know how big it is because that's what the question is. Right? The question is find the length of the square to cut out. So we don't know how big this is, let me call it a variable. Since I'm cutting out a square, I'm going to label them both x. And then I have to cut the same amount out of every corner. So I'll have another square I cut out here, another square I cut out here, and another square I cut out here. All of these will be length x because it's a square of equal size. So the idea is we're going to get rid of this whole corner by cutting out this square, and get rid of this whole corner, and get rid of this whole corner, get rid of this whole corner, and then fold up the leftover. So when we fold this all up, we'll end up with a three-dimensional box here. Now let me try and keep track of these side lengths. I said I want x to be the length of my square because that's what I'm looking for, right? Find the length of the square. But what about my leftover? Can I come up with an expression for this leftover portion here? Yeah, because when I fold this up, this is going to end up being one of my base lengths. Right? This is going to be the bottom of the box here. So when I fold this up, I need to know what this side length is so I can label this base length. So the way to figure out this side length is to take your total side length, which is 10, and subtract 2 x's because you've cut out 2 x worth. This whole distance is 10. But we've cut out an x here and an x here. So this blue length will be 10 minus 2x. And what about down here? Same thing, right? Because you had 10 to start with and you cut out an x on each side. So in the picture of my box, I can now label the length and the width and the height. This length is 10 minus 2x. This length is 10 minus 2x. And what's the height of the box? X, right? Because when you fold it up, the x becomes the height. It becomes the width. So find the length of a square to cut out that maximizes the volume. Well, here's kind of what's going on. Now let me find a formula for volume so I can maximize it. Yeah, so the volume of a box like this is length times width times height. That's the formula. Length times width times height. So in this particular case, length and width are the length and width of the base. So 10 minus 2x, 10 minus 2x, and then x is the height. So there's your formula for volume. So we do a diagram. Figured out our formula. This is all pre-calculus stuff. Now we can do the calculus, which is to actually maximize the volume. So in calculus, what do you know about maximums? Maximum. How do you find the maximum? Right, so if you're finding relative extrema, if you're finding the relative maximum, you take the derivative and set it equal to 0. You find critical numbers. Right, so the maximums for the maxima are going to come from critical numbers. The critical numbers of V. So we're going to have to take the derivative now and set it equal to 0. Probably, since this is a triple product, I'd multiply this out to make my derivative a little easier. Avoid the product rule. Let me go ahead and rewrite this. 10 minus 2x times 10 minus 2x gives me 100 minus 20x plus 4x squared. All of this gets multiplied by x. So 100x minus, I guess we'll just collect these, 40x squared plus 4x cubed. So there's my volume formula multiplied out. And like I said, to actually find the x that's going to maximize this volume, I want to take the derivative. So find the critical numbers. So V prime, the derivative of volume, will equal, yeah, so do your power rule. The 3 comes down, 12x squared, let's see, minus 80x when the 2 comes down, plus 100. Because we're trying to maximize, because the problem is about finding a maximum or minimum, I need to set this equal to 0, find the critical numbers. So I now need to solve 12x squared minus 80x plus 100 equals 0. Which I would probably do by factoring at all possible. For example, 4 goes into all of these. And then you can break it down again. Two things that multiply out to 3x squared, 3x and x. Two things that multiply out to 25. But you have to check and make sure the middle adds up. This is 15x's, this is 5x's. Does that add up to negative 20x's? You make them both negative. So it's factors. Which means I get two critical numbers, x equals 5 and x equals 5/3. Now, are both of these viable answers for x and y? Could you imagine cutting? So this would be saying x is 5 inches.
That's just cutting into 4 squares.
So if you try to cut out a 5-inch square here, out of 10 inches, you'd have to cut 5 inches here and 5 inches here. There'd be no box left. Right? You only have 10 inches left.
It's 4 squares.
So this is too big. And if you cut 5 inches out, you're going to have nothing left. 5/3 is okay, though. You can cut 5/3 out of each side. So you're tempted to tell me, I hope, that the answer is x equals 5/3 maximizes the volume. Unfortunately, you don't actually know yet whether this maximizes the volume or minimizes the volume, or if it does either. Right? Because critical numbers aren't necessarily relative extrema. You don't know if this is a maximum or minimum or nothing. So how do you test to make sure it's a maximum?
You plug it in.
For a derivative test. Here's 5/3. I want to know what happens at 1 and what happens at 2 into the derivative. Here's the factor form of the derivative. So when you plug in 1, 3 minus 5 is negative. 1 minus 5 is negative. Negative times negative. Positive. When you plug in 2, 6 minus 5 is positive. 2 minus, because 3 times 2 is 6. And then 2 minus 5 is negative. So we go from positive to negative. This is a max. Tries to put together everything that you a lot of the things at least that you learned in calculus and calculus. It's a good application section, but like I said, I'm not gonna try to stress you out about it. If you want to study it and do it for extra credit on the test, that's fine. If not, it's fine. Questions? Okay, I'll do one more. It's always kind of the same I erased step 3, but it's always kind of the same pattern. You know, you want to try and draw a picture to make sure you understand what's going on. And then this is the trickiest part here, is figuring the formula out. Right, once you have the formula, then you do the derivative and the first derivative test. That's easy. But figuring out this formula is where all the ingenuity comes in. So you're designing a cylindrical oil drum. That is to hold 200 liters of oil, which is going to require 0.2 meters cubed of volume. Find the dimensions of the cylinder. So R and H, the radius and the height. That will minimize the amount of material used to construct the drum. So, here's my picture, right? Let's try and get this down. I'm building a cylinder, basically, right? You're designing a cylindrical oil drum. So, cylinder. And it's supposed to hold 200 liters, so eventually we're going to need to use the fact that the volume of this is 0.2 meters cubed. Find the dimensions of the cylinder R and H. So my dimensions are going to be radius, R, and then height. That will minimize the amount of material used. So as far as the material used goes, basically what that means is the amount of metal, or whatever you're going to use, to construct this oil drum, and that's going to be an area. And you need to figure out how much area you're going to have to use to cover this cylinder. So the amount of material used is the same idea as surface area. So the volume in this case actually isn't what I want to find a formula for, well, isn't explicitly what I need. Okay, I don't want to maximize volume. I have a constrained volume. This has to be my volume. Okay, this is what we call a constraint. So I'm going to use this. This is going to help me. This tells me, how much I have to carry in here, but it's not what I want to derive. So what I need to derive is surface area. I need to come up with a formula for the area around this cylinder. So for example, my cylinder has a base and a top. What's the area of each of those? Pi r squared, right? So the amount of material I need here is pi r squared. Excuse me. The amount of material I need here is pi r squared. So altogether, for my formula down here, I need 2 pi r squared to cover my top and bottom. We talked about this before a bit, I don't know if you remember. But what about around the side?
2 pi r times h.
Plus 2 pi r. Because you take the circumference of this circle, which is 2 pi r, and then you multiply that by h, and that gives you the area of this.
3 pi r times
Now we have a slight problem because we have two variables. Right, so for example, if I try to derive a with respect to r, dA dr, then I would have to know I would get a chain rule that says I need to know dH dr. I don't know how height is changing with radius. So I would like to get only one variable before I take my derivative. It just makes my life easier. So what can I use to get rid of the h, say? The volume, the only other piece of information I have.
derive it.
So, what's the formula for volume of the cylinder?
2 pi r squared undo.
Um,
Oh, pi r squared.
just pi r squared h, right? The area of the base times the height. This is the volume of the cylinder. But I know my volume has to be 0.2. So I can actually isolate h by dividing by pi r squared. So my constraint tells me that h is equal to 0.2 over pi r squared. Right, this volume, this piece of information about how much I can hold in my drum, gives me a formula for h. And I can plug that in here. I'll probably simplify it a little bit just because there's things that are screaming to cancel. Right, there's a pi and at least one of the r's. You can do 2 times 0.2 and probably make that 0.4. So altogether, my formula here is that the surface area is equal to 2 pi r squared plus 0.4 over r. So this is the formula that I'm going to use when I do my derivative. So this is the pre-calculus part. Right, this is getting a function of surface area in terms of r. Now I need to actually minimize this function. So to minimize, you take the derivative and set it equal to 0, or undefined, right? Find your critical numbers. Since I'm taking the derivative, I should probably bring that r up like this. And it's easier to take the derivative if you bring the r up, because then you can do -1, the -1 in the power rule. So what's a prime here? What's the derivative of the surface area? 4 pi r. Right, because the 2 comes down, plus So I guess minus 0.4r to the negative 2. But I want this to be 0 or undefined, so I'm going to need to simplify it. You guys want to simplify this?
Well,
You can either factor and get a common denominator. They're completely equivalent. I think we've been factoring a lot in this class, so let's try factoring. If I wanted to factor this, what could I factor out?
0.4.
Yeah, well, let's not worry about the 0.4, but what about r? r to the negative 2, and what would you be left with? 4 pi r to the what? The third, right? Because when you do r to the negative 2 times r to the 3, you add the exponents and get r to the 1 back. Minus 0.4. Just pull this whole thing out. Here's your derivative. Critical numbers come from where either the numerator is 0 or where the denominator is 0. Do I care about where the denominator is 0? Do I care about r equals 0? I mean, sure, you would use very little material if you had a 0 radius, right? I mean, your drum would be invisible. But it probably wouldn't hold the volume that we need it to hold. So this is not feasible. It's not going to do what I want. But this guy I can solve. Right, if you add the 0.4 over, 4 pi r cubed equals 0.4. Divide by 4 pi. Cube root both sides. So r equals the cube root of 0.4 over 4 pi. So r is approximately equal to, I have a number. 0.316920288837. Did that in my head. Or let's round it to 2, 0.32. So you have to do 0.4 divided by 4 pi in your calculator and then take a cube. Now, what do you think? Is this our answer? Yeah, I don't actually know if this is a minimum or not. If I did everything right, it probably is. But if I screwed up somewhere, it might not be. And my first derivative test will make sure. You could do, I don't know, what's less than 0, so 0.25, 1/4. And 1, I guess. We could do 0. This will be undefined at 0, so it's fine. So the bottom's always positive. When you plug in 1/4, you'll cube 1/4, which is 1 over 64. So is pi over 16 greater than 0.4? Ooh, I don't know. That's a good question. 3/16 is greater than 0.4. No, I don't think it is. I think you get negative. Right, so if you plug in 0.25 for r, you can use your calculator, but you need to check and make sure you get negative. And then if you plug in 1 for r, 4 pi minus 4 is certainly, or minus 0.4 is certainly possible. So it checks.
So
Yeah.
when you're doing that first derivative,
Yeah.
and you're testing
Yeah.
something less than 0.32, would you have to keep it a positive number because, or could you like
Well,
test
because you have another critical number here, that would be in a whole different section. So if you didn't have this other critical number, then you would just use 0 or -1. You just don't use anything like that. But because this is another critical number, you actually have a totally different region over here that we don't want to test.
Wasn't negative numbers do it even negative material?
Yeah, but at this point I'm just doing calculus, right? So if I don't have another critical number here, then I can test this region by putting in a negative number, because it's going to behave the same here or here. I mean, it's like saying, well, I could put in 0.00001. Well, that would be stupid because you're not going to have a barrel of radius 0.00001. But the calculus would check, you know what I mean? The math works, even though you would never have a barrel of that size. But the other question is, how do I get h? Because I have r, it works out. How do I get the height now? You got to go back to your equation that you solved here. Conveniently circled, clouded, whatever, squiggled. Now for r, you probably want to plug in the unrounded or the least rounded one. But you can do either one. So I plugged in this guy. 3, 1, 9, etc. And I got 0.6338405767, approximately 0.6. So I'm not going to be super picky about the decimals at all, but just so you know what I plugged in and what I got, I wrote them on. So about 1/3 of a meter by 2/3. These problems depend a lot on these formulas, and if you don't have these formulas down, then I will try to give you on the extra credit problem, for example, the 3-dimensional formula, since I know you'll kind of be at a loss if I don't help you out here. But even if I give you this formula, knowing how to put it all together, knowing to solve for this, put it in, take the derivative, it's still quite a task. Work on those if you want. I will put one of these on the take-home quiz on Wednesday, not necessarily this one, but an optimization problem, just so you can try it. And then you won't see it again until that extra credit on the final. Question? Yes?
For this problem
Yeah.
specifically, does it matter if you, like, for example, just choose to solve for r instead of h?
Nope, you will get the same thing.
Okay.
But why would I advise against solving for r? Because you have to take the square root, and it just makes your derivative uglier. But it'll work. Yeah, the important thing is you solve for one of them so that you just have a function with one variable.